Welcome to an example on how to use Stokes' theorem to evaluate a line integral. We're given the vector field f and asked to use Stokes' theorem to evaluate the line integral along the curve C of f dot differential r, where the curve C is the triangle with vertices shown here, oriented counterclockwise as viewed from above. So if Stokes' theorem applies, the line integral along the curve C of f dot differential r is equal to the double integral over the surface S, where the curve C is the boundary of surface S, of the curl of f dot n differential S. And we'll actually evaluate the surface integral using this double integral over the region R by projecting the surface S onto the xy plane. But let's first review Stokes' theorem. Stokes' theorem states that if S is an oriented surface with unit normal vector n with a piecewise smooth closed boundary C with a positive or counterclockwise orientation, and the vector field f has components p, q, r, which all have continuous partial derivatives, then the line integral along the closed curve C of f dot differential r equals double integral over the surface S of the curl of f dot n differential S. So Stokes' theorem states a relationship between line integrals and surface integrals of a vector field. It tells us the net rotation over the surface S is equal to the net rotation on the boundary C under the given conditions. So for the next step, let's look at this graphically. The vector field f is graphed in gray, and the curve C is the curve that traces out this blue triangle in a counterclockwise orientation, or in this direction here. So this would be the curve C, and this would be the orientation, and the surface S for the surface integral would be this entire blue triangle. So for our example, Stokes' theorem does apply. So for our first step, we want to write the equation for the surface S, which again would be this blue triangle. And because we have the intercepts of the triangle, the surface S would be given by the equation x plus y plus z equals 3. Later we're going to need the function g of x comma y, which is equal to z. So if we solve this for z, we would have z equals, again, g of x comma y, which should be 3 minus x minus y. We're also going to need the partial derivatives of g with respect to x and y later, so let's go ahead and find those now. The partial derivative of g with respect to x is equal to the derivative of 3 minus x minus y with respect to x, which is negative 1. And the partial derivative of g with respect to y is equal to the derivative of 3 minus x minus y with respect to y, which is negative 1. Now let's determine the curl of the vector field f. The curl of the vector field f is equal to del crossed with the vector field f, which would give us this 3 by 3 determinant, where the first row of the unit vectors I, j, and k, the second row are the differential operators, the third row are the components of the vector field f. Using expansion by minors gives us this next line here, where for this first determinant, we eliminate the row 1 column of the I vector, which would be row 1, column 1, leaving us with these 4 elements. And then we have times I minus, for this determinant, we eliminate the row 1 column of the j vector, which is row 1, column 2. The remaining elements give us this determinant here, times j plus, for the last determinant, we eliminate the row 1 column of the k vector, which is row 1, column 3, which gives us these 4 elements. And now for each 2 by 2 determinant, we'll determine this product minus this product. Let's go ahead and write the curl of vector field f in component form, where the x component is the partial derivative of 9z plus x squared with respect to y, which would be 0, minus the partial derivative of 3y plus c squared with respect to z, that'd be 2z. Then we have minus the partial derivative of 9z plus x squared with respect to x, that's 2x, minus the partial derivative of 7x plus y squared with respect to z, that's 0. And then for the z component, we have the partial derivative of 3y plus c squared with respect to x, that would be 0, minus the partial derivative of 7x plus y squared with respect to y, that would be 2y. So simplifying, the curl of the vector field f would have an x component of negative 2z, a y component of negative 2x, and a z component of negative 2y. So going back to our first slide, We now know the curl of the vector field F. So applying Stokes' theorem, the line integral along the curve C, which is a closed curve, of f dot differential r equals the double integral over the surface S of the curl of the vector field F dot n differential S, which is equal to the double integral over the region R, where the region R is a projection of the surface S onto the xy plane, which is shown here. If we go back to our graph and look down on the xy plane, we can see this right triangle here would be the region R on the xy plane. And if we set z equal to 0 in the equation of the plane, notice how we do get x plus y equals 3, which is the equation of this line here. So right now this is over the region R. We'll come back to this when we determine the limits of integration. And now we have this dot product where first we have the curl of f, but here, because we have differential a, which is equal to dx dy or dy dx, we need to make sure the curl of f is expressed only in terms of x and y. So notice how the x component is negative 2z. So we need to substitute 3 minus x minus y for z for the x component. So we'd have angle bracket negative 2 times the quantity 3 minus x minus y, and the y and z components stay the same. And we're going to dot this with angle bracket the opposite of the partial of g with respect to x, which would be positive 1, comma the opposite of the partial of g with respect to y, which is also positive 1, and then we have a z component of 1, and then for differential a, let's use dx dy. Remember, this form of the double integral over the region R is simplifying some of the work in this form of the surface integral, but they are equal to each other. And now for limits of integration for x, we'd integrate from x equals 0 to this line. If we solve this equation for x, we'd have x equals 3 minus y. So limits of integration for x are from 0 to 3 minus y. Limits of integration for y are from 0 to 3. Let's go and evaluate this on the next slide. Let's go and distribute the negative 2 here. So the x component would be negative 6 plus 2x plus 2y. Everything else stays the same. And notice how here we just have 1 comma 1 comma 1, so the dot product is just going to be negative 6 plus 2x plus 2y minus 2x minus 2y dx dy. And this simplifies nicely. 2x minus 2x is 0. 2y minus 2y is 0. So we can go ahead and factor out the negative 6. We have negative 6 times the double integral. And we just have dx dy, if we want 1 dx dy. So we integrate with respect to x first. So the antiderivative is just x. So big F of b minus big F of a is just going to be the quantity 3 minus y minus 0. So we just have 3 minus y. And now we integrate with respect to y. So we'd have 3y minus y squared divided by 2. So when y is 3, we have 3 times 3 minus 3 squared divided by 2. And then when y is 0, both terms are 0. So we end up getting negative 6 times, this is 9 minus 9 halves, which is positive 9 halves. Here we simplify, there's 1, 2, and 2, and 3 2's and 6. So the exact value is negative 27. Which remember tells us the net rotation along the boundary curve C oriented counterclockwise, as well as over the surface S, where the unit normal vector would point outward. So going back to the graph, because the value is negative with the given orientation, the net rotation along the curve C in the counterclockwise direction, as well as the net rotation over the surface S, using the right-hand rule, would be clockwise, not counterclockwise. I hope you found this helpful.